Okay, so I have been doing some exercises to do with subobjects, monics, and pullbacks. And I want to go through these exercises, go through the solutions, and um, discuss something about how it seems that sort of general category theory is structured. I mean, we've got this result that we can describe general limits by products and equalizers. So it seems like if we have products and equalizers, that's enough to be able to talk about most concepts. Of course, then we always have the dual notion that, we need co-products and co-equalizers to talk about co-limits. But let me just talk about the sort of normal oriented view, and the dual results are obviously there. But I mean, what comes about from these exercises, which I'm going to go through? I'm basically going to say what the question is and then give the solutions. And the sort of outcome is basically that pullbacks are probably the most fundamental concepts in one of the most fundamental concepts in these basic kind of gadgetry of category theory, because what we're going to see is that we have a sort of way to define what a monic is in terms of a pullback. We have a way to define what a product is in terms of a pullback, and we have a way to define what an equalizer is in terms of a pullback. So basically, once we have pullbacks, if we have a pullback for every corner, as in every pair of arrows with the same target, then we have and we have a terminal object. Then we have finite limits. We have all finite limits present in that category, and we can construct them all because we already know how to construct any limits given products and terminal objects and equalizers. But we're going to show that we can get products and equalizers from pullbacks, and we can get monics from pullbacks. So this is really a very big deal. Now, okay, the first question then, let's work through these. So the first question is, given these pullback squares, we want to show that if this monic I is contained in this monic J, then f to the minus 1 of I, as in the pullback of I along f, is contained in f to the minus 1 of j. And we can do this just using one of our kind of pullback lemmas. The second one I talked about in the sequence of videos on pullback lemmas. And basically it's pretty straightforward. We just draw the two pullback diagrams like this. We have this, and then we assume that I is contained in J. That means I is in J. That means there exists a K such that JK equals I. So we have this purple thing, and then that results, which in McClarty's book Elementary Categories, Elementary Topos is theorem 4.9. That just gives us the proof immediately. Now, I wanted to do a recap here because there's this very interesting kind of result. I mean, we have that a pullback of a monic is a monic. I think I proved that in the Topos theory videos, or maybe in the supplementary video with it. But yeah, the pullback of a monic is a monic. That's very important. And then this result is that when we have a pullback of a monic, we have this kind of result, which really justifies it really justifies this usage of this kind of in language. What does it really mean to say that, for example, k equals f of x is in I? I mean, it's always nice to, think about what things mean in terms of set theory as well. So let's say that I look like this, for example, in the category of sets. So, it's just kind of injecting or picking out a subset of C. So what would it mean for k to be in that? Well, we have some function k. Let's say this one here, for example. And if it's in I, that means that there's a h such that IH equals k. Now, it's also interesting that since I is monic, this h here is actually unique, because if we have I h dash is also equal to k, then the fact that I is monic means that h equals h dash. So that's kind of interesting. But I mean, basically, the way we can sort of visualize this is we can just say that this monic here, I, is really just selecting a subset of, or a kind of sub-object, I suppose is the better word, of C and more generally. And I mean, what this intermediary H is basically doing, like, for example, in this set example, we have this K that's like sending stuff into C, but it's only like, because like the meaning of saying that, okay, K is actually here. The meaning of saying that K is in I, well, like formally it means that there exists a H such that IH equals K. But the kind of intuitive way we can understand it is to say that, like, all of the result, or all of the kind of outputs of K are kind of contained within this subset that is sort of swept out by I. Okay. And the way we can view this H is just doing what K does to that subset, and then I just injects it into the actual set. Okay. So anyway, we have this result that x is in f to the minus 1 of I, which is just defined to be the pullback of I along f, okay? If and only if f of x is in I. Okay, so this is the definition of a so-called inverse image. So how can we understand this result? Well, basically what it's saying is that, like, we have C here, and we have some kind of sub-object of it, which is A. And then we have some kind of arrow from B to C. And then what this f to the minus 1 of A is, this is f, I mean, it's really this kind of sub-object of B, which is just the stuff that has, like, I mean, theoretically, say it's the set of all x in B, which is, well, I mean, theoretically, you say if a set of all x that has that such that f of x is in this sub-object. So this blue would be f to the minus 1 of I. But it's very nice that this result holds for general, sort of generalized elements. And we just have that x is in f to the minus 1 of I if and only if f of x is in I. How do we prove it? Well, so we're assuming we have this pullback here. Now x is in f to the minus 1 of I. That means precisely that there exists a k such that f to the minus 1 after k is x. Now IQK is ff to the minus 1 k is fx. So since there's this qk such that IQK equals fx, we have that fx is in I. Okay, so that's this way around. Conversely, suppose fx is in I. So we have this kind of picture. Well, that means there exists an R such that IR is fx. And then we have the outer perimeter for this pullback candidate. So that means there exists a unique H such that QH equals R, and more importantly, f to the minus 1 IH equals X. So that means X is in f to the minus 1 of I. Okay, so that's all good. Also, should recap this kind of more critical result, actually, which is that the pullback of a monic is a monic. So we'll suppose that I is a monic here, and we have this kind of pullback diagram. So we want to show that this pi 2 here, which is the pullback of I along F, is a monic, okay? This is kind of justifying the type of subset-y kind of illustrations I've done here, really. So, or suppose that pi 2, which is what we want to show is monic, show that pi 2, suppose that pi 2 x equals pi 2 y, and we want to show x is y. So let's go. Well, we have that f pi 2 x is I pi 1 x just by the commuting square, and then because pi 2 x is pi 2 y, we have that that's also equal to f of pi 2 y, which is also equal to f of pi 1 y. Well, since I is monic, that gives us that pi 1 x is pi 1 y, so let's set alpha to be pi 1 x is pi 1 y, and beta to be pi 2 x is pi 2 y. And now that's the outer perimeter. And we have that I alpha equals f beta. So there has to exist this, so let me just draw this in. Well, then there has to exist this unique intermediary arrow, such that, so let's call the arrow K, such that pi 1k is alpha and pi 2k is beta. But since alpha is pi 1x is pi 1y, we could choose k to be either x or y to satisfy that. And since beta equals pi 1x equals beta equals pi 2x equals pi 2y, again we could choose x or y to be the k such that beta equals pi 2k. So we have to, so since this k is unique, we have k equals x equals y, so we're done. Now, I thought it's just very interesting, this idea that we have this inverse image thing. So I constructed this example like a cat is an animal, so is in language is a monic, and then we'll do this pullback. So a person who has a cat as their favorite animal, that is a person, and that's really the pullback of a cat as an animal along H, which has as favorite animal. So let's just illustrate this result here. Where is it? That x is in f to the minus 1 of I, if and only if f of x is in I. So let's say we have a house and x is owned by, so a house is owned by a person. So when is that going to be in this f to the minus 1 of is here. So that's a person who has a cat as their favourite animal is a person. So this function here, a house is owned by a person, is going to be in a person who has cat as their favourite animal, when every time we have the person who owns a house, that person's going to have the cat as their favourite animal. And that's obviously a false statement, because there are people who own houses that don't have cats as their favourite animals. But we see that condition, x is in f to the minus 1 of is equivalent to saying f of x is in is. So what's f of x? F of x sends a house to the favourite animal of their owner. And we're sort of saying that previous thing's equivalent to saying that that function is going to be in this is. So that would be that whenever we have this function that sends a house to the favourite animal of the owner, that animal would be a cat. Again, that's obviously false. There are houses that have owners that don't have cats as their favourite animals, but those statements are equivalent at least. Anyway, on with the exercises. So 4.2 is basically just well, we can just think of it sort of vertically, so we can just say pulling back an arrow along an identity is the arrow. More precisely, this is a pullback square. So how do we do it? Well, obviously it commutes. If we have some t with u and l, making the outer perimeter commute, then we have 1 of b after u is f after l. So we have u as fl. Now we want a h such that fh equals u. So h going down like that, so that fh is u. And 1 u is l. Sorry, 1 h is l. So 1 h is l gives us h equals l, and this fh equals u. It gives us fl equals u. So these are the conditions we need to meet. So we know just picking f of l will do that, and that also makes the outer square commute. So, and it's unique because we need it to satisfy this. So that's that one done.